Okay, sounds good. We'll just get started then. Uh, let's see. So we have Jennifer here today, and Jamie. Nice to meet you guys.
Nice to meet you. Thank you so much for hosting, George.
Yeah. So my name is George Szabo. I'm the director of solar design here at Apex Clean Energy, and I work in the renewable energy field to design solar projects. So a lot of the work that I do is around layout design, technology selection, and energy modeling. So pardon me, someone's at my door. I'll be right back. So just take a moment.
Where are you from?
Okay, what a timely interruption. All right, yeah. So yeah, on the solar design side, I'm mainly focused on energy modeling, layout design, and technology selection. So today, uh, we have a lot of opportunities to discuss layout design, materials, different types of technology, major equipment. But for today, I think it would be helpful to help set a foundation of some of the vernacular that we use a lot in the industry, as well as some key metrics that are used not just to talk about solar, but to talk about other top types of renewable energy projects, such as wind. So I have a slide deck that I actually used last month for my company that I put together to review some of those. So I'm going to share that today, and that's what we'll be walking through. If you have any questions at all, or you want to know more about something, just feel free to either raise your hand or you can interject whenever that makes sense for.
George, I just wanted to say thank you to everybody for being here. I'm sorry for the clunkiness of getting everybody here. I think we've gotten, hopefully nobody else tries to join the Google Meet, but I'm going to try to monitor it on my laptop and I'll send people this way. But thank you, George, for being here. For the students who are here, George was one of our amazing meet and greet industry folks during the RE Plus conference. high ratings from all the students that met you. They just really enjoyed talking with you. So, so I just appreciate you being here. And at the end, I know I'll have questions that I would like to ask. So I look forward to hearing more. Thank you.
Awesome. Great. Yeah, and so this session we'll probably just focus again on the vernacular, some key performance metrics, and even go through some examples. And then next time we'll probably talk more about different technology, and then maybe designing a project and how to run an energy model, stuff like that. So we'll just get going here. And I hope this all appears on the right screen. So just bear with me until we get this shared appropriately. Sorry guys, stand by. Okay. You should be seeing just a blank screen with bubbles. All right, there we go. Yeah, here we are, season 3. Okay, so we're just gonna hop on in. This presentation is brought to you by me and my cats. We got Luna and Binks and my little babies, keeping me active and sharp. Yeah, so today's agenda, we won't go over Solarium. That's like an internal Apex type of tool, but we will be going over some common energy and power examples, and then focusing on this section here about design metric basics. So pretty interesting stuff. Probably not going to go into deep detail to all of these, since this is kind of like a growing list of different definitions that I think are really important to get a handle on as you're working in this space. But let's walk through some of the important ones. Yeah, common definitions. So watt, unit of power. Megawatt hours, unit of energy. And in this slide deck, we actually go through a good example of the difference between power and energy, since you talk a lot about capacity, you talk a lot about generation in this space, and making sure that you have a good handle on the difference between those two when you're trying to describe something is really important. D-rating is the reduction in the nominal output of equipment. DC is direct current power that comes out of the modules. And someone refers to this or megawatts power. It's often seen as, in this format where you have the subscript of power. They're often referring to the amount of modules on a project. Modules are panels, are PV. AC, this is the power that comes out of the inverter. When someone refers to this, you'll need to clarify if they're referring to the total nominal inverter output or the grid limit. So often when we're talking about the design or the capacity of a project, we're referring to a 100 megawatt project. That 100 megawatts is typically the interconnection limit, or the maximum output that the project can put onto the grid in a given hour. But as like we mentioned earlier, nominal inverter output is the nameplate value of an inverter. We'll go in a little bit more about that later. Capacity most often refers to the interconnection grid limit in megawatts AC. Capacity also defines the size of a project, unless otherwise stated. So because the quantity of DC that you have on a project is always higher than your AC. So these are like your capacity with regards to DC and AC are both different. Interconnection or grid limit is the maximum power that can be injected into the electrical grid it shouldn't say at any given time, it should say over the course of 1 hour. And we're going to go into this more, but net capacity factor is the ratio of plant generation to plant capacity over a year. So NCF is a description about how well a project can satisfy its interconnection limit. If you had a 100 megawatt AC plant and you could provide 100 megawatts every hour over the course of an entire year, your NCF would be 100%. That's the easy example. But that's not how solar works. We do not generate power at night. So there's only a portion of the day in which the plant could possibly produce power, and it ramps up. It has less generation in the mornings and the evenings, and you see your maximum generation around noon or the zenith. Solar plants typically have an NCF of around 25% to 32% on the high end. You can get lower NCFs and higher NCFs, but you really need exceptional solar resource to get to those levels. Or conversely, poor solar resource. If you're the further away you are from the equator, typically the worse your solar resource is. Modules per string. It's the quantity of modules that can be wired in series for a particular project and inverter. Modules per string is a function of ambient weather conditions, module characteristics, and inverter characteristics. We could do some examples of calculations with calculating your minimum and maximum module per string, but we're just going to get through this list and then go over to some examples. Specific yield, we'll talk about in a second. It's a performance, it's a quantitative performance metric. 8760s, you hear this in the lot. This is like a lot in the industry, 8760s. But for those keen, this is the quantity of hours in a given year. But it also refers to a particular production metric. Often it's generation that people care about the most. But you could have temperature, you could have auxiliary power over the course of the year. It's really just describing a type of parameter that's measured over each hour over the course of a year. One hind portrait, two hind portrait. These are abbreviations to describe different module orientations. So we've got total nominal AC capacity, total nameplate capacity in the inverters. I'm going to speed up actually a little bit because I don't want us to run out of time and get to the good stuff. Injection capacity is analogous to grid limit. Large format modules. They're just modules, then they're just straight up bigger. You'll see a lot of modules out in the world today, even exceeding 700 watts, but those aren't to be confused with modules that necessarily have a efficiency advantage. It's just that their footprint is physically larger, so they collectively can produce more watts. But the module intensity, which is an important metric that I don't actually state here, is something that is important to take a look at. And that's your module wattage over the actual surface area of that module. And you'll see that, between modules that are large format that have much higher wattage ratings, the module intensity largely hasn't changed because the efficiency hasn't changed that much. We're in the era right now of cycling out of PERC as a type of technology into TOPCon, which is a newer type of technology that is available for monocrystalline modules. We're not going to see another large technology jump until we get into heterojunction and perovskite. Those are like the future tech of modules that are going to come out in the next couple of years. Basis of design is like your starting reference, parcel acreage, buildable area, facility space. That's kind of like internal to Apex. DC to AC ratio is the ratio of the installed direct current power over the injection limit or alternative current. In other words, it's the total power in megawatts DC over your grid limit. Common DC to AC ratios for solar plants are 1.2 to 1.4. We could talk a lot about why you want to overload your project with high DC, but basically modules are impacted by light-induced degradation and light attenuated degradation. So the longer they are exposed to sunlight, the more impure the glass and absorption material becomes, to say it simply. An easy way to think about this is an old car. If you look at the headlights, they might have yellow on them, and you can use a substance to kind of clear that up and polish it up. That's an example of light-induced degradation. Modules don't get yellow because the glass that they use on the front side is very, very pure. It has a super low iron content. Because all of that iron within that glass adds a little bit of reflectivity to it, which we don't like. But it also leads to like really low degradation over the course of the module's lifetime. DC degradation is relative to the degradation of the modules. And all modules nowadays have about a 30-year linear power warranty on them. It's very difficult to measure that in the field realistically, but they do have a power warranty up to 30 years. Most project lives for utility scale projects are into the 40-year range. So while the linear power warranty only goes up to 30 years, the expectation is that the module will actually live to 40 years and beyond. Most modules have an annual degradation of about 0.40% per year. That's just their linear degradation. So by the end of 20 plus years, you're going to have 80% or more of the power coming out of the modules, which can be repurposed for other uses or used to repower the solar facility. Okay, we're gonna skip sub-hourly clipping. That one's kind of complicated to go through. Yeah, we'll skip over BESS and battery management systems. Economic curtailment's a good one, but we'll talk about curtailment another day. Okay, let's see. Substation, primary role of a substation. So you have two major facilities other than your PV fields on a solar farm, if you're thinking about the utility scale size. One of them is a substation. And the primary role of a substation is to elevate the voltage that you're getting from your medium voltage collection system to match whatever the grid voltage is. So most medium voltage circuits, so you have your low voltage side of the system. That's like your modules. Low voltage will be low all the way through till you get to your inverter. And technically, the power coming out of an inverter is also low. It's about 650 volts, maybe 690, maybe a little bit lower. But out of the inverter, you're going to go straight into the medium voltage transformer. And from that medium voltage transformer, the standard voltage range is 34.5 kV. But we need to bump this up to high voltage. This is medium voltage. We need to scale it up even further to go up to a generation step-up transformer. So you have little medium voltage transformers, but then you have a generation step up. And generation really just refers to the class of voltage that the power is being elevated to. So you need a substation to achieve that, and the various types of equipment that are required to do so. After a substation, though, you then have a switch yard, and the primary role of the switch yard is to interconnect the solar facility to the transmission line. So you have these massive structures called GOABs, which are gang-operated air brakes. Yeah. And you might have seen some videos of these. You can look up, GOAB, GOAB on YouTube, and you'll find these pretty wild videos of these massive structures kind of like turning into some metal and these huge arcs of electricity jumping in between the two. So you can see like exactly what the purpose of a switchyard is in real time. Pretty exciting event. Like electrifying your solar facility. Yeah, switchyard, window, drain tiles, energy yield assessments, technical due diligence. Yeah, we'll talk about those later. Okay, let's talk a little bit about energy, work, potential, kinetic energy, and power, and then we're going to go through some examples. And are we only going to 3 o'clock today?
No, we have a full hour if we want it.
Okay, cool. I'll try to slow down. I might need to
Yeah,
pause
I think
and
we
just
were
make sure I'm
planning
not.
to have the presentation be more like 30 minutes so that we can have time for Q&A, but
Okay.
you need it, you have
Perfect.
extra.
Excellent. That'll be great. Well, I'll try to get through at least this example then, and then we'll talk about like we'll see what our time is at. Okay. All right. So let's talk about energy. Energy is the ability to do work. Examples of this are heat, light, motion, electrical, chemical, gravitational. So from energy, and we all kind of know this, but this is a really good reminder about how these interact with each other. Energy is broken up into potential and kinetic. Potential is stored, and kinetic is working energy. And the common units of these are megawatt hours, horsepower, calories, and joules. It's less common, but kind of fun units are Rydberg units, barrels of oil, and BTUs. But there's a lot of different types of units regards to energy. Work. The transfer of energy to an object when a force is applied as it's displaced. These are all kind of very specific conditions in which we describe when work is done. An example is pushing a box and the box slides. If you push a box and the box doesn't slide, technically no work is actually done upon the box, even though you're putting in energy. Potential energy. Energy stored in an object due to its position relative to a neutral position. Example is dropping a ball and the ball falls to the floor. This can also be considered gravitational potential. Sometimes people refer to just potential energy as gravitational potential. Kinetic energy is the energy of motion. Potential energy, kinetic. Power, and this is where we're going to get into our examples here, is how fast energy is used or transmitted. The amount of energy divided by the time it took to use or create the energy. So we have our energy up here, right? What were our common units? Megawatt hours. So you take that You take that. I mean, ignore the mega. Like mega is just, 10 to the 6 watts. So if it's just watt hours, and you divide that by the time it takes you to create that energy, that's your power. Boom. Easy. What type of energy do photovoltaics produce? It's both. Which is it's pretty cool. It's very cool. By the way, we have an Animals of Apex chat channel, which is where all these lovely little creatures appear on my slides. So in case you're curious. All right. So let's break it down. What's the difference between power and energy again? We kind of just talked about it, but let's see more examples. Energy is the ability to do work such as running and jumping. Power, how fast energy is used or transmitted. So power is a rate. Energy is watt times time. Good example is megawatt hours. Power is energy, that energy again divided by the time. This is the rate of energy being used, or megawatts. Lifting a box requires the same amount of energy no matter how fast it is raised. Lifting it faster requires more power. Let's let that one sink in for a minute, because I think it's a very helpful and powerful statement. Kinetic energy to raise the box. Boxes also gain potential energy being at this height. Technically, it's that energy is stored because we're holding on to it. Okay, forgot I added this. Sure, test your knowledge. Let's see. In 1983 sci-fi adventure, Return to the Jedi, when Palpatine was roasting Jedi Master Luke Skywalker like a marshmallow with force lightning, was he correct in claiming unlimited power, or should he said unlimited energy?
Energy.
Lightning, whether from a cloud or the creepy tendrils of the fingertips of a Sith Lord, is measured in joules, or a unit of energy. Unable to live with Palpatine's mistake, Lord Vader knew this and took necessary actions. Okay.
I love it.
We'll skip over solarium stuff. That's just for the company thingy, but let's see. You know what? I thought we had the examples in here. I'm sorry. Let me take a quick look at the type of metric examples I was looking for. Oh, never mind. They were here. Literally the next slide. Okay, back on. All right. So we'll try to spend about 5 minutes on this, but there's like really there's 3 really important metrics that if you're learning anything from today, this is what you're going to want to capture. And I can send this over too, so you guys have this as an example. Net capacity factor. Okay. This is used very often to describe the efficacy of a generating facility. So it's a quality metric that indicates how much of the injection capacity is supported throughout the year. We had that example earlier, but equation's super easy. It's plant generation in megawatt hours over 8760 times the plant megawatt AC injection capacity. Again, that 8760 is just a conversion for year into hours, because this plant generation that we have up here is in years. Here's that example from earlier. If you had a generation facility producing all the injection capacity throughout the entire year, NCF would be 100%. And then, yeah, typical solar facility NCF 25 to 31. So here's some examples with some numbers. So if you have a 100 megawatt AC facility, you're typically going to have a DC to AC ratio of 1.35. So that would yield you a DC to AC ratio, or excuse me, a megawatts DC of 135. And this is high level. And let's say after you've ran your energy analysis that you're going to be generating 240,000 megawatt hours in year one. Degradation happens though, so you have to specify year one. So your NCF is going to be 240 divided by 8760 times 100, and you're getting an NCF of 27.4%. And that is net capacity.
Can I interrupt? I don't know any of this stuff. I'm not an engineer. These students on the call probably are like, this is a good review. I don't know. They probably know a lot more than me. What dictates your megawatts AC? Is that just
so the megawatts, so the injection limit for a facility comes very, very early in the plant design. So And it can come from a variety of sources, but we have a transmission team, and it's their job to help find opportunities for injection capacity. A lot of the time, what you're doing is that you're entering into a massive queue of other developers and independent power producers trying to add projects onto the electrical grid. Each of those projects need to go through a very lengthy review period with the power market. So whether maybe that's ERCOT or MISO or PJM, and they have to coordinate with an independent system operator. They're called ISOs, independent system operator, to get officially into the project queue. So in most cases, we are told we have 100 megawatts or 200 megawatts or 250 megawatts to try and build a project within this area to connect into this type of market. Other times, so that's the most typical scenario, is that we will be given our allotted capacity from the transmission team, because that's what we've entered into the interconnection queue for. So there's a big queue if you're a power generating facility to actually get and connect onto the grid. Another type of option, if maybe that doesn't exist, maybe you're not going into a queue and you can be into it's kind of like an open RFP or a request for proposal. So most, how should I say this? Most power markets have a renewable energy portfolio mandate. Renewable energy portfolio mandate. And that says that a particular power producer or like a major utility has to have a certain quantity of the power that they're generating come from renewable sources. California has a super strong renewable energy portfolio that mandates a substantial amount of the state's power come from renewable energy sources. Not just solar, it can be hydro, wind, geothermal. Solar is definitely a big part of it as well. So in that case, what a utility company may do is open up and say, all right, well, we have 1,000 megawatts or 1 gigawatt worth of power that we need to basically buy for next year, for 2025. So different types of independent power producers, like Apex and other companies can come in and say, okay, great. Thank you for opening up this RFP process. We're going to submit a handful of projects that we've been developing within this state to enter into this bidding process. In that case, the injection capacity actually kind of has a moving target. We might submit several designs to try to satisfy the needs best for the utility that's managing the RFP. But typically it gets issued to us by the transmission team, so we know what target is that we're trying to hit. Great question. Okay, we're going to kind of graze over this one because I want to get to the 2 other metrics that are really important. But similar to NCF, you have something that's referred to as specific yield or specific production. This is just for solar. There's not, like, NCF is a universal type of metric that can be used to describe any type of generating facilities capacity, but specific yield just focuses, it's very similar. Instead of using AC as the denominator, now we're using the DC. So we have our plant generation like we had before, but now we are ranking that against the DC, or the amount of panels that we're installing. And typically specific yield and NCF can be inversely related, because if you increase your DC on a project site, your specific yield is actually going to go down, because the purpose of an interconnection limit is to limit the amount of power that we are exporting onto the grid at any one time. That happens because the grid needs to manage, needs to have certain expectations for the power entering the grid. So that being said, you're going to be clipping power more if you're adding more DC onto a plant. And clipping is just a way to describe, this was your maximum injection limit. You're producing this amount of power, and that delta, that's your clipped power. That can be captured in things like energy storage units, but often it's just lost. Anywho, okay, this is the other important metric, which is the DC to AC ratio. Don't say AC DC. You're going to look silly. Don't do that. But the DC is the installed DC capacity for the facility. This is the total sum of the quantity of modules multiplied by their wattage class. So we're going to go through an example here. And then AC side is the maximum injection limit of the generating facility. We use this a lot. So given our example before, if we have a 100 megawatt AC facility, the module wattage is 600 watts, and we have 225,000 of them. Our power in megawatts DC is 135. So our DC to AC ratio is 135. This was my friend's dog's birthday. They turned 6. Okay, so DC to AC ratio. And the reason that I want to emphasize that is because there's also the inverter loading ratio, which is a metric of DC over a metric of AC. But this is where it's important to understand the difference. And why we also mentioned nominal inverter power before. So ILR, inverter loading ratio, you're still using the same DC. It's the installed DC capacity for the facility. It's the total sum of the quantity of modules multiplied by their wattage class, and it's the same DC as before. The nominal AC, and this is on the denominator, is the total or individual nameplate output of an inverter. So you're going to have a bunch of inverters on a project site. The size of an inverter that we're using right now, there's also two classes of inverters. You have string inverters and you have central inverters. We'll save that for the next one. But your inverter, so if your inverter nominal output is 4.4 megawatts, or this could also be considered MVA. We'll also do a lesson on the power triangle. That one's going to be really fun, I promise you. But inverter quantities, we're going to need about 26 of these. So our total nominal megawatts AC is 114.4, which, as you notice, is higher than our injection capacity. So why would we want to have more nominal or nameplate power from the inverters? Well, there are reactive power requirements at a solar facility. The majority, if not all, of utility scale solar farms are required to be capable of supporting plus or minus 0.95 liter lag power factor. For those that have a deep background in electrical design, we'll kind of know what that means, but we'll talk about that later. Basically, what it means is that the solar facility needs to be capable of taking voltage off of the grid, but also being able to put more voltage on the grid, which helps with voltage regulation. Part of that is the reactive power effort that can be output by inverters. Now, if there are three types of power. There's apparent, real, and reactive. Real does the work. Apparent is the hypotenuse of the triangle, and then reactive is, your Y. So real is the base. You have real, reactive, hypotenuse is apparent. When you produce more reactive power to add voltage to the grid, that takes away from your real power. So you need to have a little bit of overhead room on your inverters to actually be able to support the grid requirements. Now, it's not only upon the requirements of the inverter to be able to provide reactive power support, because you can also use capacitor banks, but it's quite commonly used. So in this example, our DC is 135 divided by 114.4, and our ILR is 1.18. Nominal AC capacity is always higher than injection capacity due to derating real power caused by temperature, elevation, and reactive power support. Okay, last example, and then we'll pause and take some questions. Ground coverage ratio. This is also my friend's dog. I'm obsessed with this thing. It looks like a doll. Ground coverage ratio. So this is an important metric to understand the spatial relationship on a solar farm. GCR is the ratio of the module length over the distance or pitch between two adjacent rows. So majority of the time we work with single axis trackers that are oriented in the north-south direction, but this applies to anything really. It can provide, it can be fixed tilt as well. So in this example, these are two single axis trackers. We know that because we are presented with a rotation angle here. And I should have put a north arrow into the page because we're looking north. We're looking up the rack. And this is the rotation angle as the module rotates throughout the day. The common range of motion is like plus or minus 52 degrees. And that's what you would expect out of a single axis tracker. So the ground coverage ratio, GCR, is that module length. So this right here in blue, that's our module. It's that module length over the pitch, which is the distance in between the adjacent rows. So you could actually measure the pitch on a number of points. It's pretty typical to go pile to pile, which are right here. So if your module length is 3.8 feet, they're that big, they're huge nowadays. Over 24.5, which might be your pitch, your GCR is about 32%. Higher GCR means that your racking is closer together. If it's closer together, a couple things are going to happen. One is that, well, all modern day single axis trackers operate on a backtracking system. It's a backtracking algorithm. So that means that if there is a rack adjacent to your rack and it begins to shade your rack, this is actually going to tilt to a shallower angle to avoid shade on the adjacent rack. That's a backtracking algorithm. But you want to avoid triggering that early, because imagine, that your sun's over here, right? This white area on my screen, that's the sun. You want your modules to be pointing direct normal to the sun. Direct normal being just 90 degrees. That's where you're going to get your highest level of transmittance of photons through the module. But if you have to then tilt away because you don't want to be shading this row in the back, this rack is now producing slightly less power because it is less direct normal to that source of light.
But I guess it's less
Good.
than it was shaded. Because if it was shaded, it would be
Yes.
less, but it's not as.
Yes, exactly.
Less
Yeah, it's an overall net gain. But the closer your rack is together, the earlier that backtracking algorithm has to kick in. So a higher GCR, you get higher near shading losses. In addition, which I didn't mention here, you also get a smaller bifaciality window. So just to talk about that for like a second, I know we're eating into question time, but it's a good topic to discuss. So your bifaciality window, modern day solar modules are all bifacial, which means they have collector cells on both the front and back side. A funny thing as well is I thought that bifacial modules were like a joke and that they'd never catch on in the industry. And now it's like the industry standard. You hardly see any monofacial products being available. Man, I am not able to. Oh, here we go. Finally. Okay. So if you have really tight row to row spacing, your bifacial window is really small. So pretending again that like this is the sun, your bifacial window is any amount of space that allows light to travel, bounce off of the ground and onto your modules. So all of this is your bifaciality window, they call it. These are different type of like light rays. So the tighter it is, the less bifacial gain you also get on the system.
And then the other thing, George, just to interject, is with that ratio, do you need to consider larger ratios also when you are looking at agrivoltaics, things like grazing or and things like that?
Right. So you actually you want lower. So the lower the ratio, the further apart your racks are, you get a lower near shade loss and higher generation. It's directly proportional. But yeah, if you do have agrivoltaics, and we actually just had a really good webinar that I need to finish watching. I was busy, but some of the things that you need in agrivoltaics is, yeah, you do need some type of sufficient clear row space, but you also need the racking to actually be a little bit higher off of the ground. So another important metric that we have is the module clearance height. And this is typically 1.5 feet. So when the module's tilted at its full range of motion, you would have 1.5 feet on that lower edge to the ground. We don't want that to interfere certainly with any type of vegetation. But one, it's not going to be ideal for the plants to have that obstruction. And then two, we don't want the lower edge of our modules shaded due to that vegetation. So with agrivoltaics, it might be considered to add a little bit of additional length onto the piles themselves. The piles being the foundation piece that holds the rack together to elevate the entire rack up higher. Great. And let's see. Oh yeah, we're at questions now.
I guess with that, sorry to interrupt again, but with the added height in order to, get away from the vegetation or the sheep or whatever, I assume that's added cost. And then because you have to space them out more, then you have less production at higher cost. So where's the where do you draw the line from an economic benefit for that?
Right. Well, again, if your racks are spaced out further, it's going to be better for generation. Similarly, if your racks are elevated, that's also better for generation. But it does require additional steel length because as much as you add above ground, you also have to add below ground, if not more, to counteract your moment of rotation or the point at which the entire thing is just going to bend over. So agrivoltaic still is pretty experimental on the utility side, but we are advancing more projects forward that are part of our DER project design. So that is, DER are distributed energy projects where the power is used often immediately and doesn't really go onto the grid. But for those types of applications, we were able to, manage that space with various types of approved livestock that could be situated on the farm. But I'm not an expert just yet until in agrivoltaics, and we're seeking opportunities to find how it could be more applicable because it certainly is. It's very utopian, and I absolutely love the concept of growing your food and raising different types of animals and things, and then also have a power generating facility on top of that. It's incredible. That's really exciting stuff. So I'm hoping that it'll continue to gain momentum because vegetation management also, just to talk about cost, vegetation management is extraordinarily expensive. Going and mowing 1,000 acres, it costs a lot. But if you are raising sheep that can handle that responsibility, it's funny. You actually just take out the lawnmower and add in, a couple flocks of sheep and you rotate them around the project site and you're good to go. Obviously, there are still costs there. It's not all 100% gain, but the concept alone is really incredible. And
I've
sheep
heard the term landscaping, which I think is so cute. Landscaping instead of land.
Landscaping. Oh, I love it. Haven't heard that one coined yet, but I'm a fan already. Yeah. Sheep are excellent. They're some of the perfect animals. They're super docile. They don't nibble on wires. They're fairly obedient. They don't weigh enough that they're not going to rub into anything and cause damage. And they're not agile enough to jump onto the modules and start playing on them like goats do. So yeah.
Oh, the goats. They're cute, but they suck when it comes to solar.
True. Okay. Well, I'll stop sharing then for a little bit, just help provide some time for some questions.
Awesome. Well, thanks, George. That was really fascinating. I learned a lot. Thank you very much. Jamie and Jennifer, I'll leave it up to you guys if you have any questions, but otherwise I have some questions of my own I'm happy to ask later.
I have one.
Yeah, sure. You're a little soft. I don't know if that's near you, but.
Is this a little bit better?
Yeah, thank you.
Okay.
Yes.
So yeah, I'm just thinking, I really enjoyed when you were talking about your transmission team kind of coordinating with the local regional ISOs to coordinate connecting into the larger grids. I'm not as familiar, but I was just curious, when we're connecting into a larger grid, is it on the responsibility on the larger grid side that's already established, or when you're adding to it, what types of field device monitoring might be used to ensure that there's proper power quality coming out of the generators, I guess into the grid, or kind of that interface? I'm kind of curious about.
So there's a lot of SCADA. SCADA it's kind of collectively, it's a system of different types of reporting that are provided to different types of ROCs or ROCCs. ROCs are remote operating control centers that monitor the health of a system. so they know exactly how much power is being produced. And then they can even measure, you know, like we have full visibility on what's happening at the project site. If a single inverter goes offline, we know about it. If we know that the grid is, let's say that a power line goes out because someone bumped into it, and we know that the plant needs to react by providing additional support to the power grid, it can do that in real time. And we have people monitoring the system health 24/7. There's always people there. It's kind of like NASA, where they got that big room with the big screens, and everything's kind of connected together, and you see this massive power flow model. All that's real. It's pretty wild. And all that's provided by various types of SCADA systems, which are different monitoring measures that are located all around the project site so that the entire project site can speak to each other. You have SCADA devices on each inverter. A lot of the substation typically have them on the operation and maintenance building as well, to house some of that sensitive equipment.
Yeah, because I'm aware, like for IBR dominant systems, oscillations can be a bigger issue. So I'm just like, yeah, I guess like that real-time monitoring of if you start seeing an oscillation, go a little wary, like you don't like the way that waveform's looking, that they have to take a deeper look into it.
Yes, yeah. And if they need to activate something like the reactive power mechanisms of the inverter or dip into the capacitor bank, that's something that can be achieved at that time as well.
Ooh, thank you.
George, I've got a quick question about that
Yeah.
slide that we ended on, where like the general like module. Sorry, I think I'm in the sun. The general module layout.
Mhm.
I'm wondering, is it feasible to like vertically offset the modules so that you reduce that near shade loss, or does that just get too high too quick, and then it's just not possible?
Right. So you want to try to keep them as flat as possible. Like if you have a project site and it's either due south or flat is your best case scenario. Because if you do elevate one, or if you do like elevate the adjacent row, you're only going to be paying the piper in the afternoon when the sun's on the other side, and the range of motion for your modules has drifted from your morning setting all the way to your afternoon setting. So keeping them flat is ideal. There are different types of advanced backtracking algorithms to help, though, to further support the standard type of backtracking that takes into account row to row losses due to elevation differences. It's a specialized type of energy analytics that can be done once you have a lot more details about a project. But there are more modern ways of trying to capture additional sunlight.
Awesome. Thanks so much.
George, something that I noticed, this is my funky fault of all this. Thank you so much for everything and for being willing to share the slides, because
this did not record because I started Zoom by accident first.
I think it is recording still. It says recording on the top right.
Oh, it is recording? Okay, so maybe it is. I don't know. But anyway, if it is not recording, as the host, you're the person who can click record. But if you see it recording, that's awesome.
Yeah, if it comes available to me, I'll I can stop recording and see if it starts to synthesize.
Yeah. Awesome. Sorry about that. I promise next time it's going to go so much better, guys. Jamie, thanks for that really good question. Can you remind me, I haven't met you before. Where do you go to school?
Yeah, of course. I'm at Vanderbilt, so I'm studying mechanical engineering there.
Awesome. Well, thanks for joining us today.
Absolutely.
I really enjoyed learning all about the system design and the solar details. George, do you guys use helioscope for your for doing a lot of your system design work, or do you guys use a different software package?
Yeah, so the standard industry software for energy modeling is the big one. Like there's lots of different design softwares out there to help accelerate like actually drawing the facilities. So in that respect, helioscope can do both. You can both draw the facility and use it to measure generation. But we use PVSys, which is like the OG of energy modeling softwares. Again, I'll just type it out, but it's PVSys, like that. there hasn't been enough momentum until recently by one of the independent engineers that we work with. Because banks basically, like, that's what you need to align with, is when you go out for a project, you need to secure debt, a lot of it, for a project. And you do that with a combination of money provided by the company, money provided by banks, and then available money from tax equity. So what those other two components use to like validate whether the project is going to be successful or not is based off of PVsyst. DNV has recently released a version. DNV is a independent engineer, and they do a lot of work in the solar field and wind as well. They've released a version, a new like energy model version that they're going to be using going forward that just does more things than PVsyst. PVsyst has been around forever, but also updates really, really slowly. And there's certain needs and demands that the industry requires, and PVsyst just isn't there yet. So we use that. We don't use Helioscope for actually designing the project. We use CAD in conjunction with a software called PVCase. PVCase just helps us iterate on the project design faster by allowing us to say, you know, if we have this big box, okay, but I want to test different ground coverage ratios within that box, and then I want to measure how much DC I'm getting from each of these variations in GCR. That's the type of tool PVCase is really great for, as well as talking directly with PVsyst. So we can do something like export our entire project design and load that into PVsyst to get a more accurate near shading loss, because we have the actual design in there with the topo, with like the topography, the elevation differences, and near shading objects like trees. So those are like the two main, like plus CAD, I guess, is the are like the main softwares that we use. One for energy modeling, one for layout design.
Thank you. Do you guys have any other questions? I know we only have like 5 minutes left, and not to hog the space, but I wanted to make sure at the beginning of the call, I didn't have a chance to tell you about some of the Repowering Schools programs that you may want to be paying attention to from that student side. And then George, I'd also love to, the reason we're recording it is because we're trying to put together what we call career stories, which are like kind of canned questions that industry answers about the where they are in their career and how they got there. And if we could just ask a couple of those, if you, Jen, and Jamie need to leave, you know, George and I can do those on our own for a couple of minutes. But those are the only two things that I wanted to take care of. So for you guys, Jamie and Jennifer, just so you know that we have a couple of opportunities coming up that you may want to know about. The first one is we have a distributed wind energy conference that happens in February in DC. Not sure how easy it is for you all to get out in February to a conference, but we are going to be hosting a student symposium. And so we're looking for students to apply and let us know what kind of research they're doing that they would like to share at this conference. We have like an industry poster session, but you also get opportunities to do an oral presentation. This year, maybe to the industry, but usually in years past, it's at least been like peer review, like presenting to each other. We do a field trip, and then we bring in speakers to talk to you about things that are relevant to you and the research that you're doing. So it's a fun couple of days. And when you apply to come to the student symposium, we can at least provide your hotel accommodations. So that's something we can do. Yes, Jennifer.
Yeah, I was actually looking on your website earlier. Would you be able to drop the link for the application? Because I wasn't sure if I was like qualified or not to possibly do it. And I was very interested. Yeah, I did see the DEWIA conference coming up. I attended the PNNL Distributed Wind Summit a few weeks ago, so they shouted that out.
Oh, awesome. Yeah, I don't think I will be able to put it in the chat just because I'm between things, but if you're on, already signed up on the list to receive these notifications, when George sends me the slides, I can send this and those announcements out to you as well.
All right, thank you.
Yeah, and then there was a second thing that I wanted to, we also in January, so we have annual Renewable Energy Education Awards. So in January, we're going to open up nominations, but this is the time to kind of be thinking about it. We give out awards for student excellence, so you can totally self-nominate. But we also give out awards for educators. And so if you have any professors that you work with that you like really you know, think are amazing and are doing wonderful, wonderful things to support you. We'd love to recognize them. And then if you love George, you can always nominate Apex for for a industry champion award as well. And then we also give recognition to schools, colleges, universities, and K-12 schools that have wind and solar on their campus, but are also teaching about wind and solar in the classroom. So that it's not just sitting on a rooftop somewhere and forgotten, but it's integrated into the curriculum. So we, all of those great things, and I'll send the link out to the page where you can look at all of the different nomination areas, and it's free to nominate. And again, you can self-nominate. Yes, thanks for making sure they know how to spell your name when they nominate you. That's great. Yeah, so those were the two announcements that I want to make. But like I said, I'll send a follow-up email with the information on how to contact George if he's okay with you reaching out to him, and also share his slides if he's okay with that.
Yeah, absolutely. That won't be a problem at all. I was going to offer, you know, I've talked a lot with folks one-on-one if they kind of need some guidance to try to figure out how to enter into the job market or enter into the world. We could talk about that. I think next time that we meet, ahead of the meeting, Remy, I'll provide you, just because I have so much content that I've created over the years, I'll just build up with what I've done in the past and kind of like what makes sense. So next time I'll just give you a list of different agenda topics. Then if folks are interested in that, then it makes more sense to pull them in and attend. But I imagine the next time we'll be talking a lot about different technologies that are necessary for a solar farm to operate, and eventually we'll get into design.
Yeah.
Awesome. Well, that's amazing, George. We really appreciate you being here. And like I said, that's all I have, other than just a couple of kind of career focused questions for George. If y'all want to stick around and hear the answers, otherwise we can send out the recording later.
Gotcha. Yeah, this was a great opportunity. It was really a pleasure meeting you both.
Awesome. Well, George, like I said, we've been doing something called career stories, and the idea was to interview industry folks with kind of the same set of questions, so we get to hear across the board people in different stages of their career, different in parts of the industry. And so the first one, which I'm sure you said at the beginning of the call, but just to kind of get it recorded again, was just to tell us about yourself, where you work, what your job is.
Sorry, Remy. I'd actually love to dive into that, but I have a follow-up meeting with with our project management team. So that's all the time I have today, and I apologize. Oh, I think you're on mute, but
I completely understand. Happy to do it another time if you don't mind.
Yeah, just let me know when it works for you, and I'll be sure to hop on. But I gotta hop. Make sure to send data, Remy.
Thank you, everybody. I'll follow up as soon as I can. Thank you.